All right. This video is going to be over basic bonding rules and finishing up a little bit of the covalent bonds. I will make a separate video each for molecular Lewis structures and structural formulas. So if you're looking for that information, it's not in this video. Now, that said, let's get started. All right, there's two kinds of covalent compounds, polar and nonpolar. The difference between them depends on their structure. Mainly it's because of their structure. But it is also the result of how they actually wind up forming their bonds. So, let's talk about polar and nonpolar. First off, a polar molecule you're extremely familiar with is water. Okay, so water has a negative, that's a plus sign, a negative end by the oxygen, and it has positive ends by the hydrogen. Okay, this is a result, we've talked about this before, but we haven't actually talked about why. Okay, this is a result of something called electronegativity, which I'm going to write up here, and I want you to add to your notes. Okay, electronegativity. And I feel like I wrote this too small, so let's see if you can actually read that. Yeah, you should be able to read that. Okay. Electronegativity is the tendency, this you need to add in, I'm not going to write all this down. Electronegativity is the tendency of an atom to gather electrons. The tendency of an atom to gather electrons. Or repel them. An atom with a high electronegativity gathers electrons strongly. An atom with an extremely low electronegativity repels them strongly. Oxygen is one of the highest electronegativities out there. And that has to do with its structure, but you don't need to worry about that much. Just know that oxygen has an extremely high electronegativity. It collects electrons like a kid on Halloween collecting candy. It goes around and cannot get enough of them. It is more than happy to collect electrons. Hydrogen is more like the grandma at the door who's like, "Ooh, take them. Here, take it. Have it. Take all the candy you want. Take all the electrons you want. Take them off my hands. I don't want them." So as a result, whenever you have an oxygen in a compound, a lot of electrons wind up spending a lot of time around that oxygen, which makes the oxygen a negative region of the molecule. And the hydrogens in a molecule tend to end up with a slight positive charge. This is one of the things that causes hydrogen bonding, which we talked about when we did bond types. Hydrogen bonding does not only form between hydrogen and oxygen. It can be between hydrogen and just about any element, but it is usually hydrogen. That's why we call it hydrogen bonding. So that's polar. Nonpolar is when this doesn't happen. Or a lot of molecules are considered nonpolar because it doesn't appear to happen. And a really good example of this is carbon dioxide. So, CO2 is symmetrical. Now, so is water, you might say, but it's symmetrical in the line between the positive and negative regions. So if we draw a line between the positive part of water and the negative part of water, it's not symmetrical. The oxygen is on one side, the hydrogens are on the other side. so it's not symmetrical. Carbon dioxide has two borders, one here and one here, because carbon is what ends up being slightly positive. Now, since the carbon is flanked on either side by an oxygen, it still ends up with polar regions, but they cancel each other out so well that it acts nonpolar. This is why carbon dioxide doesn't dissolve well in water. This is why soda, if you leave it sit out, it will naturally go flat, because what makes it carbonated is the CO2 that's dissolved in the water. And so if it's not kept under pressure, that CO2 will very, very quickly boil away or fizz away. So these two kinds of compounds do not get along. A lot of compounds out there are nonpolar. In particular, lipids. Lipids tend to be nonpolar, which is why they don't like water. But there are only 7 truly nonpolar compounds out there. And they are not actually considered compounds. And that's because a compound has to consist of 2 different elements, and these do not. So they are actually called diatomic atoms. And there are 7 of them. And I'm going to pause this and prep a periodic table since I can't point at the big one on the other side of the room for this video. So I will be right back. All right. The magic 7, as my chemistry teacher called them, are the only 7 elements on the periodic table capable of forming a truly diatomic. Good Lord. A truly non-polar molecule. This is an example, by the way. All of these are examples of molecules that are not necessarily compounds. So if you're wondering why we spent the time on that distinction, this is one reason why. So, hang on. I'm going to turn the other light on so this is easier to see. All right, let's see. That's a little better. All right. So, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all clustered together, and they form a nice little 7. But if you look, there are only 6 of them there. That is because the 7th is hydrogen. So the 7th one is all the way over here. But these 7 elements that I've outlined are the only elements on the periodic table capable of forming a diatomic atom. They're the only 7 that form truly nonpolar molecules. Everything else is polar, but acts nonpolar. Okay? So you need to list these down. So I'll say them again. Hydrogen, nitrogen, oxygen, fluorine, and the U comes before the O in fluorine, chlorine, bromine, and iodine. List those under diatomics. You can list the element symbol or the name. I don't care. They're your notes, but you need to know them. And that brings us to our bonding rules. So let's talk about how bonds actually form. I'm going to scroll down a little bit and erase some of the stuff on the board. So this is your last chance to get anything copied down from the top part of the screen. Okay, so let's talk bonding rules. Now, since there are 2 types of real compounds, ionic and covalent, we have 2 different sets of bonding rules. I'm going to cover ionic, but you don't need to be too terribly familiar with these. These are the ones you really need to worry about right now. But I'm going to cover these first because they are also important and will be excellent test questions. So, pay attention. Number 1, positive ions can only form a bond with a negative ion. So, for example, aluminum, which has a positive 3 charge, cannot form a bond with another metal because all metals form positive ions. Instead, it has to bond with negative ions. Now, that could be a nonmetal or It can also be a polyatomic ion, which is what I'm going to use as my example. So aluminum will frequently bond with hydroxide to form aluminum hydroxide, which has the formula AlOH3, because there is one aluminum and 3 hydroxides. So what happens is this aluminum finds 3 hydroxide ions, each one with a -1 charge. And oh so conveniently, there are 3 -1s and 1 +3, so they cancel each other out. And so we still have a neutral molecule or compound. The total charge is 0. Okay? Now, how this actually happens, we talked about when we did ionic bonds. So if you want to go back and look at bond types video, I'll walk a little bit through how this tends to actually happen with molecules when they're or with atoms that are ionizing. Okay, but that's the main thing for ionic bonds. Now, covalent. First off, remember a covalent bond requires 2 electrons instead of the 1 that an ionic bond requires. Because here, the hydroxides can just steal an electron from the aluminum to get their electron, and that forms the bond. Over here, we're actually sharing electrons, which means that we actually have a little more cooperation going on, but the bonding is a little more complicated too. Where's my blue? There it is. So I'm going to put up another diagram, a simplified Bohr. I'm going to first put up the water molecule that we used before. Which water has 2 hydrogens, so we have a circle for each hydrogen as well. Can you see that green? Not well. Okay, I won't use green anymore. That was terrible. Hang on. There we go. All right, so we have an oxygen with 1, 2, 3, 4, 5, 6 electrons, as it should when it's neutral. And we have 2 hydrogens, each of which have only 1 electron. However, if we look at their outer shells here, oxygen actually has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. And both hydrogens have 2. So with this method, they actually managed to share their electrons and still fulfill that requirement. So then another one of these, an example would be ammonia, which is another compound. And this is the one I needed that green marker for, so I'm going to use a red instead, since I seem to recall you could see that. Except I'm going to pause it this time to draw it to save a little time. Okay, so here is an ammonia atom where we have nitrogen at the core with 3 hydrogens attached to it. The nitrogen has 1, 2, 3, 4, 5 electrons, as it should, and each hydrogen has 1. But again, by overlapping their electron shells and sharing their electrons, you can see that their outer energy levels are all satisfied. Okay? Now, this is called a simplified Bohr diagram. And this is not something that I'm actually going to have you drawing. It is something I'm going to be expecting you to be able to recognize and read. So on a future test or quiz, for example, you might have to actually look at one of these and tell me something about it. So you need to be familiar with them when you're looking at them. Downsides of simplified Bohr diagrams: you cannot tell or you cannot represent multi-bonds between elements, okay, which is one of the things we'll talk about in the next video where we're doing Lewis structures. Multi-bonds can make things a little more complicated, so we have to use a different kind of diagram. Okay, so 2 electrons are being used in each bond. 1 is coming from each element, and none of them are making more than 4 bonds. The nitrogen is making 3, the oxygen is making 2, and each of the hydrogens have made 1. Okay, but none of them is making more than 4 bonds. Now, in this class, there are only 2 elements you have to worry about that can make more than 4 bonds. Okay, those are going to be carbon and silicon. I would highlight carbon and silicon. Well, not silicon. Highlight carbon because you're not really going to actually see silicon in here much. But carbon, you're going to deal with a lot. So you need to remember that carbon can make 4 bonds. And that is because it's in group 14. It has 4 valence electrons. And we'll review that more when we do molecular Lewis. Okay, the last thing I want to go through is I want to talk a little bit about the types of electrons, which I will be drawing a picture up here when I do that. And you'll want to definitely take a picture or a screenshot of that. So I'm going to pause this and prep, and we'll be ready to go. Okay, this is a dot diagram for oxygen, and below it another one for hydrogen. And I'm going to be using these to kind of show off what I'm talking about here. So first off, electrons always work in pairs. How many of you know one of those people who just can't be single? They have to be dating somebody. Okay? Electrons are like those people. Okay? They just have to be with somebody. They can't stand being single. They have to be paired up with someone. So because of that, they tend to pair up. And I'm going to be using some dating examples for this to try to make this a little bit more memorable. And we'll see how that works. So first off, we have lone pairs. So these two and these two would be really good examples of lone pairs. Lone pairs are kind of like the old married couples that we all know, where they're super happy together. They just spend all their time together, and they're content. They don't date. They don't break up. They don't get in arguments. They're just happy. Okay, lone pairs are like those people. Okay, they don't break up. They're not moving around much. They just hang out. Now, in an atom, a lone pair has to exist in the same atom. I said in an atom. In a molecule, they have to exist in the same atom. You cannot have a lone pair where one electron comes from one atom and the other electron comes from the other atom. Okay? The second kind is going to be unpaired electrons. Okay, unpaired electrons are single electrons. So these are our old married. You probably can't see that. Right? Old married couple. And these ones are single. So these are electrons that haven't found a partner, and they're very, very upset about it. They really, really want to find somebody. Okay? This is one of the other things that can cause bonding. Atoms want a full outer shell, electrons want to be paired up. Now, what can happen is, if you have 2 single electrons from different atoms who get close enough to each other, they can actually form a bond. Okay? Now, these 2 electrons would be dating. So these are a bond pair. And these are the electrons which are dating. It might work out, it might not. They're never going to turn into a lone pair, I can tell you that much. But they might stay together for a really long time, or they might be together for a couple of minutes and then go, yeah, this ain't working, and break up. But these are your bond pair, they're your dating electrons. So we have unpaired, which are single, lone pairs, which are the old married couples, and bond pairs, which are the couples that are dating. Right? Those are your different kinds of electrons. Here is some extra information you can copy down. One thing I want you to add here on bond pair, they must come from different atoms. Okay, a bond pair, each electron must come from a different atom. Here one came from the oxygen and one came from the hydrogen. So remember that, they have to come from a different atom. While in a lone pair, they must be in the same atom. Okay, that is going to be it for this video. Next, I'm going to be putting up one over molecular Lewis structures, and then after that, we'll do structural formulas. But this is it for this one. Pause it, rewind, go back through it if you need help, and email me if it's not making sense. Have a wonderful night.